Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning, everyone. Today we will examine ocean acidification and why it matters for both ecosystems and human societies. Ocean acidification is the long-term decrease in the pH of seawater, caused primarily by the uptake of anthropogenic carbon dioxide from the atmosphere into the ocean. When carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers pH and reduces the concentration of carbonate ions that many marine organisms need to build shells and skeletons. Calcifying organisms such as corals, mollusks, and some plankton rely on carbonate ions to form calcium carbonate structures. The availability of these ions is often expressed as aragonite or calcite saturation states, which are critical measures for shell formation. To make this concrete, consider pteropods, sometimes called sea butterflies. These tiny planktonic mollusks form thin aragonite shells and are a key food source for fish species in polar ecosystems. Experiments show that lower aragonite saturation can dissolve their shells and increase mortality. Another good example is coral reefs. In controlled mesocosm experiments, corals exposed to lower pH levels show reduced calcification, slower growth, and greater susceptibility to disease. This compromises reef structure and the biodiversity reef support. There are also regional differences. The Arctic is especially vulnerable because cold water holds more carbon dioxide and because the buffering capacity is low. In contrast, subtropical gyres have higher buffering, but face other stressors like warming and nutrient changes. Now, I want to draw your attention to socioeconomic consequences. Scientific studies and fisheries reports have documented impacts on commercial shellfish industries. For example, in the Pacific Northwest, hatcheries experienced larval oyster losses linked to corrosive water chemistry over a decade ago. In the Pacific Northwest, the shellfish industry has already experienced declines linked to acidified waters and lost millions of dollars in harvests. These economic effects occur because juvenile shellfish are particularly sensitive to changes in carbonate chemistry. Reduced survival at early stages means lower yields and higher costs for hatchery managers who must monitor and modify water chemistry. Beyond calcifiers, there are potential indirect effects across food webs. Changes in plankton communities can alter food availability for fish and marine mammals. Changes in nutrient cycles and microbial processes also affect primary productivity, which underpins fisheries. Researchers use multiple methods to study ocean acidification. Observational time series from moorings and ships measure pH and carbon system parameters over decades. Mesocosm experiments manipulate pH to test organism responses, and biogeochemical models project future changes under different emission scenarios. A useful case study is the North Atlantic Time Series at the Bermuda Atlantic Time Series site. This long-term dataset revealed steady declines in carbonate ion concentration, corresponding with increasing atmospheric CO2. Model projections suggest that if carbon emissions continue on the current trajectory, many shelf seas will reach aragonite undersaturation by the end of the century, at least episodically. This implies more frequent conditions that harm calcifiers. There are also interacting stresses to consider: ocean warming, deoxygenation, and nutrient pollution, can amplify or modulate the effects of acidification. For example, warming can increase metabolic rates, which raises energy demand for organisms already struggling to calcify. What can be done about it? Mitigation of carbon emissions is the only global solution to stop the root cause of acidification. Regional adaptation measures are also important. These include selective breeding for resilient shellfish strains, hatchery water treatment, and local nutrient management to reduce harmful algal blooms. Another potential approach is blue carbon restoration, such as restoring seagrass beds and coastal marshes. These habitats can sequester carbon and locally alter pH through photosynthesis, creating refuges for sensitive organisms. Finally, policy responses require integrating science with economics and community needs. Monitoring programs must be expanded and translated into actionable thresholds that managers can use to protect both ecosystems and livelihoods. In summary, ocean acidification is a pervasive and growing problem that affects chemistry, biology, and human economies. It requires coordinated research, mitigation, and adaptation efforts to reduce future risks. That concludes the lecture. I will take questions now.
Listen again to part of the lecture. Then answer the question.
In the Pacific Northwest, the shellfish industry has already experienced declines linked to acidified waters and lost millions of dollars in harvests.
For more TOEFL mock tests as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day. AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.